And Marissa, do you do edits to the video before it's posted? Okay.
Yeah, I will.
Okay. So we can cut our banter out from the beginning.
Absolutely, yeah.
Oh, so we have 14 people on. My thought is that we just give it a couple minutes after 5:30 for people to come on, and then we'll get started.
Sounds good.
You know, I say I don't get on social media, but then I'm constantly on LinkedIn, and I noticed one of the products that at one company I was at, we were going to buy, bought the other product that was recommended. So in case anybody is interested, Next Caller was bought by Pin Drop. So pretty neat. I heard that they had some coinciding things, but they were basically the function we were looking at was user authentication that was coinciding, but they had some more advanced things on the pin drop side. So just interesting. All right, so we're 2 after, so guess we'll go ahead and get started. Welcome everybody to the, what month is it? It's hard to tell with this pandemic going on. The March ISSA meeting. It's crazy, we're already a year into this pandemic. Hopefully everybody will be able to get vaccinated shortly and we'll be able to resume in-person meetings at some point, maybe one day. Well, with that said, I want to go ahead and introduce our speaker today, Peter Staarfanger. He is former vice president and president of the ISSA organization here. Peter, I'm going to go ahead and turn it over to you.
Thank you, Nigel. All right, let's see if I can work this thing correctly. All right, all my Zoom experts, grit your teeth. Here we go. All right, is there anyone who can't see my screen? Okay, good. Let's get started. All right, so today I'm going to talk to you about digital forensics applied to containers. And specifically, this will be focused on how do we enhance intruder dilemma. And the way that you know this is a container talk is that you can see the Docker whale in the upper corner with the sleuth hat on. So just to kind of put it out there, anything you see today is really, look, it's out there, it's open, it's on the internet. This is definitely not a reflection of anything that my employer or my associates do in practice. But again, it is representative of just, again, what's openly out there and just what I've experimented with from a hands-on keyboard perspective. A little bit about me. We're not going to spend a lot of time here. We got a lot of great content for you, and that's not really centered on myself, but effectively, I've been doing this for approximately 15 years now. And really the only thing you should get from what's in front of you is just that, you know, during that time, I've tried to balance both my personal growth as well as being involved in the community. And of course, making sure that, you know, my employer and their needs are taken care of. And so just kind of digging right into things, here's kind of an overview of what the flow is going to look like. We're going to talk about what are some of the threats to Docker or containerization in general, like right now, what's been happening. We're also going to compare containers versus virtual machines. I got to tell you, when I first started digging in, this really gave me a lot of trouble. So really happy to be able to share my understanding at this point. We're also going to talk about what a typical Docker environment looks like, and of course, how some of the security that's built in, and then some of the additional add-ons, if you will, that are available for purposes of Docker security. And then once we kind of have that level set as a group, then we'll dig into what our opportunities are from a forensic analysis perspective and how it is we create that intruder dilemma. So let's dig right in. All right, so as far as Docker threats, I really just kind of wanted to lay things out on a timeline because, you know, just a couple of years ago, I got to tell you, the cadence of Docker related stuff was kind of slow. And I feel like things kind of kicked off. You know, we had some security conferences out there where, you know, because Docker was growing in popularity, you know, security researchers really started to pay attention to it. And kind of what they found was that, you know, from a Docker point of view, from a containerization point of view, that because that technology was so young, people were, you know, spinning up and using it in such a way that really, if you network exposed it, anybody from the internet, from your network, could easily interface with your environment and do bad things. And so that was kind of what researchers were releasing, you know, back in late 2017. And then what we saw from 2017 through mid 2018 was that, you know, when it comes to Docker, Docker is based on, you know, a image sort of technology where you go out to registry and you kind of pick, you know, the platform that you need to run your application on, and you pull from these registries, and of course run your code on top of it. Well, the provider Docker, their Pacific registry ended up hosting, you know, over 17 different backdoored images. And again, this was for almost a year, and that ended up putting thousands of these compromised containers out into the world. And things just kind of got worse from there. You know, we ended up seeing things like, you know, as an example, you know, we can see that, you know, in our timeline, all of a sudden, you know, we have coin miners popping up that are out there, auto propagating themselves via these exposed Docker APIs on the internet. You know, we started to see things that were a little more scary, where you know, the malware was even smarter in the sense that, you know, when these open APIs were found, the malware, of course, would deploy itself and then create persistence in such a way that again, you know, when we think in terms of Docker, you know, Docker is typically very ephemeral and it's very short-lived. Well, the malware ended up abusing some of the underlying normal conventions of the host of this Docker service to continue persisting way past the normal lifetime of any container that was running in memory. And really, as we proceed through time, you know, these self-propagating mechanisms, you know, it really started to look like the way that Docker was being abused, even leading up till now, starts to very much look like an internet worm, where we have everything from the SSH keys that are left on the host of the Docker service being grabbed and used to propagate down to our AWS GCP, Azure credentials being snatched up. And again, this Docker-based exploitation, using that to self-propagate, this malicious software. So let's talk about, what it means when we say, the use of, containerization, or specifically Docker. And, to me, I think the hair that's worth splitting is just talking about the difference between virtualization versus containerization. And from a virtualization perspective, generally what we're familiar with is that we kind of have a type 1 or type 2 sort of virtualization. And from a type 1 perspective, this is typically, as an example, if you have something like a VMware ESX, where again, the host operating system is directly running all your virtualized guests. And that's, again, a type 1 type configuration. And typically at home, we might see something like a type 2 setup. And that's really where, again, we have our, maybe our laptop or desktop. And then on top of that, again, we have whatever our favorite flavor of operating system is. And then something like maybe a VMware workstation or a Hyper-V running. And then our guest machines are running on top of it. And what's important to really say about virtualization is that, if we imagine, metaphorically, that we had a pie, effectively with virtualization, we're cutting up that pie and we're dedicating our hardware resources to whatever the running virtual machine is that's, operating on top of that host, on top of the hypervisor. Well, where containerization is different is that with containerization, it's a little different. It's more like there's a pie and everybody has a spoon, and you can dig in as much as you want. And what that means to us is that, from a containerization point of view, we're no longer reserving, resources like our processors, our memory, and our storage, and dedicating that to these containers. Rather, we spin up the container, and the container, if we don't put limits in place, kind of has free reign on how much resource it does consume. Some other ways that containerization is different is that when we think in terms of the host, again, we still need our hardware, we still need our operating system, but on top of the operating system, again, we have, some kind of a container runtime engine. And that container runtime engine is operating these containers inside user space in memory. And typically what's packed inside of our containers is usually whatever binaries or libraries are needed. As an example, let's say you were an app developer and you wrote an app that's meant to run in Python. Well, you would go out and you would find a image that already had the Python framework and libraries that you specifically needed for your app to operate. And you would just add a little bit of configuration on top of that to say, well, my app code is here, please run it. And the advantage that's created for our developers is that now we can more predictably run our apps, because the container, or containerization kind of guarantees that we'll have the right runtime libraries available in order for our code to operate. And from a system administrator point of view, you're not worried about, do I have enough of the pie left to run another one of these containers? Rather, your containers just run. And if you're responsible, of course, you do, try to limit how much they can consume. But the point is that, whatever the host has available is just generally available for all those containers. Well, let's look at what an actual Docker environment might look like. And so in front of you, I kind of have it broken down, into little swim lanes to indicate, maybe some of the different major components of a Docker-based environment. And, what I want to kind of point to is that typically there's a Docker client. And really what I want you to know about the Docker client is, this is really just a binary that you're running, a tool that you're running to interact with the Docker engine, okay? And typically we're doing such things as, either building images, we're potentially pushing images to something called a registry, or we're pulling images down from our registry onto the host that has our Docker engine to be later ran as what we would call a container. And when we look at the Docker engine, again, these components I was just kind of spelling out, a lot of them reside there. And I think the biggest thing we just need to recognize is everything comes down to, yes, consistently you'll have the Docker daemon, but kind of in addition to that, on the host, you'll always have some images that are sitting locally, which are effectively all those libraries and runtime components needed for an app to run. And any of the running images, again, we recognize that as containers. And all those containers, when they're loaded into memory, really they're using, again, a runtime environment, which is making all the necessary kernel functions available. And of course, presenting again, the libraries and binaries that are made available through the image file, to that developer's code. Other things that we might find on a host that is running a Docker engine may also include a Docker file. And what's a Docker file? A Docker file is really just our infrastructure as code. You'll also hear the actual file referred to as a manifest. And really, it just spells out in plain English, in a way that we can read and understand exactly, what base image is needed. So as an example, I mentioned earlier Python. So you might say, hey, I need a Docker image that has Python libraries. And then you may have some additional code that says, also, I need these 3 tools loaded, and also my code is over here. And again, all that would be put inside of a manifest that we call a Docker file. And we'll talk about this more in detail later, but effectively, we use our Docker client to build our Docker file. The Docker file becomes an image. We store our images typically in a registry or in some kind of an artifact repo. In order to get a container, again, we have to pull that image down to somewhere where we have a container runtime environment. In this example, it's Docker. And then when we run the image, now we use the term container. All right, let's take a closer look. So from a Docker point of view, the way that we end up creating, some of the security with Docker is that, Docker heavily uses something called C groups or control groups. And control groups really are what allow Docker to constrain the amount of resources that can be consumed by a running container. Additionally, you typically have isolation in memory, and that isolation is created by something called a namespace. And a namespace can isolate everything from the way that the running container sees the actual underlying file system, what processes it can actually see in memory. We can even isolate the container so far that the container is actually only able to see, its own code and its own necessary libraries. Other kinds of isolation that go on are things like, we talk about UTS and, just to make that very simple for us, the underlying host, as an example, can have its own identity on the network environment, its own host name, versus from the running container's point of view, it's its own computer and it has its own host name. And kind of this idea, this isolation that's created by namespace is really what makes containerization work. When the container is running, it truly believes that it is the only thing running on that host and it cannot see the host, unless of course we configure it wrong. So moving on, so when we talk about some of our other security opportunities as far as how we're using Docker, there are several technologies that are available, and a lot of this is dictated, as far as availability of these components can be dictated by the underlying operating system. As an example, right in the beginning of the list, we mentioned SE Linux. And what SE Linux, if you were using, say, Red Hat or CentOS, those particular operating systems will actually have a lot of these add-ons, if you will, already installed with the Docker environment once you install it onto a host. And so SE Linux in this particular example, what it changes, on that host is that instead of having a file system with, discretionary access control, you actually end up invoking mandatory access control. And the power here is that, if you use, again, I mentioned, Red Hat CentOS as an example, there's already a targeted policy that's been written for the Docker engine that out of the gate limits what system resources a particular container can use. There are other ways that, of course, you can use SE Linux. You can definitely run it in a mode called unconfined, and unconfined really just removes any of the restraints that would be put in place by the mandatory access control that you would be creating by using SE Linux. And of course, you also have an option to define your own policies through something called MCS. And this is probably something better done by the developer, maybe not your ops folks, because with MCS, again, now you would get into custom defining what the app exactly needs on the underlying host, if anything. Other options include App Armor. App Armors where we can now specify what folders and binaries can actually be accessed on the host if something does need to be accessed locally. We can also use seccomp. Seccomp is another control where you can limit the kind of system calls that are able to be made by the container. Bringing these three, just these three technologies together can greatly strengthen the container. However, again, just to kind of move back to a point I've been raising subtly, typically, for a production environment, it's usually best that, the developer is kind of solving for this instead of an administrator, if you will, trying to, effectively analyze the running app and figure out how to apply security to it later. Now, we did talk about hypervisor and virtualization earlier. With that being said, even though we were identifying their differences, a hypervisor actually can bring some additional security, to the container environment. And specifically, the reason why, our hypervisors, our virtualization technology is so powerful is that, we're adding additional abstraction between the actual host versus the potential containers that might be running on top of it. Again, if we play back in our minds, what it is we've talked about so far, whether it's the code itself that our developers have written, or potentially the underlying libraries and binaries that code is dependent on, all those things create a particular attack surface area that could be abused. And so if we ever do have a situation where a container is abused and maybe it's configured in such a way that it's running, in a privileged mode, container escapes are really easy. And so if we're invoking, again, hypervisor, now we're introducing an additional layer that allows us to maintain control of the host. Other options include, use of, IP tables, and also either SSH or mutual authentication if we are network exposing our Docker API. As I was describing earlier, in the Docker environment, typically, again, you have, somewhere there is a Docker client, this Docker binary where we're interacting, with that engine. Well, if we want to do that over TCP IP, the minute we expose that port, there is nothing built into the Docker technology that deals with AAA type services where we're identifying and authenticating who it is that's interacting with that API. And so again, from a administration point of view, we have to add some additional layers of security. And again, you can achieve that with either TLS or SSH. Other kind of rules of thumb, not a great idea. Earlier we were kind of, describing what, the runtime environment looks like. And we talked about namespaces where, again, in memory, we're isolating what resources, the container actually has access to. And we're trying to create the perception for the container that it's its own computer and there's nothing else out there. Well, if we run in a privileged mode, which is an option both from a Docker file perspective when we're building our image, or even a runtime argument, the minute we invoke that, we effectively give root level access back to the host, which kind of violates, if you will, the whole purpose for using containerization, or at least the security aspects of it. And finally, there's an option for something called rootless, and rootless really kind of knocks out these top 3 security controls, which again would, in the best case scenario, be fine-tuned by your developers of whatever microservice is being created. And the reason why kind of make these other ones a little void is that rootless actually changes where the root file system, if you will, that the container is running from. And again, that does create its own security, because now all those underlying binaries and directories where maybe there is opportunity for exploitation if somebody were to abuse a container, well, that's now removed from the attacker. And again, we are reducing our attack surface area. All right, moving right along. All right, so what does this mean to us from a forensic analysis perspective? This is definitely not the a talk for development or administration or ops, but rather I think what's important is that all those things that I previously mentioned, we have to consider that in the grand scheme of how it is we tackle analysis of the containerized environment. All those choices by the developer to invoke, whether it's app armor or just simply how it is we limit, the amount of memory or the number of processors that can be used, by a particular container. All those configuration items have a direct impact on how it is we might consider, if we are coming into an environment that's been compromised, how it might have been compromised. And really all the things we know, and again, this is all, kind of open, this is from NIST, and this is just kind of describing maybe some of the process you might go through from a forensic analysis perspective. And then, again, we have our classic, kill chain, and when it comes to a forensic analysis point of view, we're trying to put that story back together. And by being cognizant, of all those, security configuration items, all the way back to the development side, up to the ops side, again, it gets a lot easier to start figuring out, well, what exactly was done from a tools, technique, and procedure perspective to create the exact condition that led to exploitation of the environment. And here's our traditional pyramid of pain. And if we can get down to TTP, now we're able to really invoke a lot of pain on our adversaries. So moving forward, so what are these new layers of forensic analysis? Well, first off, we talked quite a bit about this earlier. We have our system components, which again, the 3 major components are, where is the Docker engine? Where are the registries that are serving the environment? And again, where are the clients actually being run from? And then also just from a containerization point of view, again, we have our own unique artifacts. And, we talked about that Docker file, and effectively that Docker file being our infrastructure as code, our manifest, if you will, for what might go inside of an image. We have the image itself, which is really just a big old tarball that has all the binaries, code, and anything that's necessary in order for an app to run as a container. And then finally, we have this thing called a container, which is really just that image loaded into memory. So taking a quick look, when we think about those system components, when it comes to the Docker engine, some of the major artifacts are available to us right on disk, include things like, the actual runtime configuration. Typically this is found underneath, ISSA, inetd. There's actually a file called Docker, and inside that file, you'll actually see the script that's going to invoke that Docker, engine running. And, within this file, and please don't feel like you have to write anything down. When we wrap this thing up, I'm going to give everyone a little 2-pager cheat sheet, and it shows you exactly where you have to go look for all these things. But the point is that, we can look at the script that invokes the Docker, engine, and find, everything from the administrator's choice as far as, are we making, the Docker engine TCP IP accessible? Where are the logs at? You name it. There's also the Docker runtime environment, and there's a lot of great things here. This is going to be underneath var run Docker. And for those of you who are familiar with, again, the folder var and then run, we know that a lot of our necessary, configuration items, data, things like that might be found there. And what's specific to Docker is that we can actually find full manifest, it's a big blob, it's a big data blob that tell us everything that's necessary for that container to actually run in memory. And so from a forensic analysis perspective, if you're talking to, your DevOps folks, right, they're going to tell you, oh, again, this ephemeral talk, there's nothing to be found. How would you ever see this? Well, the way that you would see this is that everything that defines all those binaries, libraries, etc., again, that's going to be right inside that var run Docker folder. A lot of good stuff there. Also, our Docker versioning, again, we're showing in that timeline, and I didn't go through every item in there. And again, that'll certainly be there for you to peruse with article links and CVEs and all those things you might want to look at. But again, the Docker version is also, recorded on the system. And again, that can be found underneath, var lib Docker, and right in there is our actual versioning. And you can use that as an analyst to look back and say, okay, for the particular engine that's running on this host, are there known vulnerabilities by checking, again, things like the National Vulnerability Database. Also Docker root, so far, as far as my experimentation, again, everything seems to be underneath var lib Docker. A majority, of all of our action is going to be underneath there. And that's everything from, as I list over here on the right, the actual images that have been downloaded to that particular host, the containers that have executed over time, something that Docker doesn't do. And again, this is kind of a misnomer, is that Docker on its own does not do garbage cleanup. So if we have an image that's ever been loaded into memory and attained container status, again, any changes that happen to that file system, all that you will find on disk. So, other things that we can find too, there's also a secrets folder, and again, that's gonna be underneath var run. So if we're trying to assess, blast radius, let's say, from an analysis point of view, maybe what's brought you there is that, you had an EDR solution that understood containerization, and you could see that, that container was able to reach back and actually touch the host file system. Well, at that moment, any secrets that are on the system, to include the Docker engine secrets, are now at risk. And so, again, from an analyst point of view, you definitely just want to take a look, if you already know that your blast radius includes that the host might have been put at risk. Again, we already kind of addressed this, within that Docker root. Again, we're going to find our image listing, and we'll dig into this some more later. But image listing and containers and all that, we'll also be able to see what storage drivers are in effect. And the reason why this is particularly important to us is that right off the Docker root, you'll have a reference to the exact file system that was being used in order to build that tarball that is the image. And the storage driver really dictates how that tarball is unraveled and presented into memory. And of course, that's going to dictate to us as analysts how it is we might be able to go about things we're familiar with, like file system analysis. Finally, just kind of wrapping things up, when it comes to the Docker IP config, again, if we're looking underneath systemd, there's a file, it's docker.service. Inside this file, or even in etc docker, there's another file called daemon.json. Both these files in pretty plain English spell out for you if, again, the Docker daemon was IP enabled. And then finally, when it comes to the Docker API itself, Hopefully, we hope for this. It's just, depending on where or who you're doing incident response for, it is possible that there are not host firewalls in play. But if there are, again, be sure to check var log messages or var log UFW, assuming the unified firewall is being used. And again, those traditional places will record Docker API interactions, from an IP point of view. Okay, just a couple more, system components. Again, the registry itself, what I saw is that in a lot of the examples that I ended up working through, the registry is typically ran as a container itself. However, one thing that's special about containers is that you can give them permanent storage. And so when you give a container, permanent storage, what I found with registries is that var lib registry is literally the folder where everything is being kept at. And so we call that the root folder. And underneath, again, our registry folder, we can find, again, all the initial uploads of images. If somebody was building and uploading maybe malicious images to a local registry, we also have something called an image manifest. And really what that is, it's just almost like a phone book, if you will, for all the images that are being stored in that registry. And so that's really valuable for us as forensicators, because usually, if you're coming in on the forensic side, right, we're totally in that post-mortem space, or we're right in the middle of the incident. And usually there's some other indicator that's led you to that host. And so you do have that time frame to kind of reference if the machine that you're coming into does have a registry on it as well. And finally, I mentioned the blobs being out there as far as what, tarballs were uploaded when somebody, built their Docker file. But again, we have the repository where, the images are kind of stored the same way that you would see them on any of the Docker, hosts with the Docker engine, that download an image. And so you could actually, from a registry point of view, you have almost that full history of every version, of an image that was created, which can aid you. Let's say the registry isn't compromised, it could still aid you in doing differential analysis and saying, okay, well, I know this container went rogue, but what made it go rogue? Well, if we can, do a diff between the image, that the container was built from, then we can just clearly see what additional binaries may have been added, possibly by an attacker. Other things to consider, when it comes to Docker client, if you see that Docker client out there, and again, literally the file is called Docker or docker.exe, immediately, we do want to look for things like, certain keywords that do potentially lead us to where, let's say, as an example, one of the items in the timeline was, an early RCE vulnerability, I think being released by a group called Aqua Security. And what Aqua Security was talking about was something called shadow containers. And shadow containers, the way it relates to this particular portion of the presentation, is that the idea was if you had a developer who, again, they would probably have some local dev environment, if they were out surfing the internet just through their browser, because of the way the same origin policy works, you could exploit the Docker service through the browser. And so if there was that kind of exploitation, that would still require invocation of the Docker tool. It's also possible that, again, you could have just had a team member whose, credentials were hijacked, and, now one of these adversaries has gotten in the environment. The point is if they invoke the Docker tool locally, there are a lot of keywords that we can just, do a search on and use, to identify, that level of compromise. Some sensitive phrases, as an example, is, Docker space run, Docker exec. What would indicate is that we're actually going to execute a specific binary on a particular container. There's also other commands like Docker rm, which would be deleting. That would mean you would actually be deleting a container. Docker rmi, which is where you're deleting images. These are just some of the many that are going to be in the cheat sheet and available for you. But the bottom line is that there are certain sequences of commands that do allow for both persistence, covering tracks, all the way to, lateral movement. And so, again, that'll be available to you through the cheat sheet. Critical areas to kind of use some of those keywords that I'm providing to you include things like unallocated slack and swap space. If we get a copy of memory, even if you don't have great memory analysis tools, or maybe, the version of memory you got isn't in the best condition, so you can't really analyze it, you could still do this keyword search and kind of brute audit it, especially in the free space, what Docker commands may have been issued against that host. And that will give you a lot of clues because effectively you're getting the runtime configuration of what has been run on that device. Other things that you can look for as well, let's say we do have a developer machine, or maybe we got right on top of a host right when we thought an adversary was interacting with it. Well, hey, go hit that profile. If we're out there using any kind of shell type interaction, that's going to be recorded in the history file, as well as as an example, Vim history. Every time we do any kind of command line edits, all that is recorded almost like a flight recorder, if you will, right there, in the profile that was compromised. Just kind of other things you may want to look for from a Docker client perspective. If we spot Docker client, you might as well go look. There's a hidden folder. It's .docker, and underneath .docker is where you'll actually find all the credentials that were being used by the developer through the environment, which again will kind of help you, figure out blast radius. In addition to, of course, looking and seeing again if there was a Docker engine, what secrets are there. And so again, look for the .docker, which is a hidden folder. All the goods are there in a JSON file, which really just means for our purpose that it's pretty human readable. And then finally, when it comes to infrastructure as code, we'll dig at this more later. And I've decided to pass on some of this. There's something called Docker Compose. I'm going to save that for another talk. So if you guys are energized by this one, please let me know. I'd love to come back and talk to you about the CI/CD environment or forensic opportunities there. But most importantly, the Docker file itself, we're going to get in and definitely talk about its structure. But when it comes to, the forensic analysis side, I think what we need to consider as far as, system components are concerned is that if there are any edits, on a Docker file, again, the name of the file is probably going to be Docker file. If you carve the file system and the header is Docker file, somebody probably did some local work with that Docker file. And so again, kind of the same rules apply, right? We want to look at the user identity that was used, and then checking that profile home. Again, look at Vim history, check for things like Git interactions, look for Git directories, curl commands, Git commands. All those are valuable things worth carving and searching for to kind of help you rebuild the story. After our adversary got that foothold, what did they do next? Okay, moving right along. Quick time check here. All right. Just want to kind of dig into, again, a Docker file and just tell you a little bit about what it looks like. And I think, for your eyes, again, this presentation is going to be available. Here's a wonderful link. You can go learn this stuff. But I think what I want you to know for our purpose is that if there is a Docker file, again, more than likely it's going to be named Docker file. And then in that Docker file, again, we're going to see a header. It says Docker file. And typically there's these sections, one of them is from. What from tells us, again, is what base image we used to make the environment. I was using Python as an example earlier. And then, over on the right, I actually have, where I screenshotted, a working Docker file. And we can see here that, in this example, the developer who's making this manifest said from, and they said Python image, and then version 3 of that Python image. That's all it says. And so for us as analysts, I think what's useful there is that we can see the exact version or the exact image that everything was built from if we do find a Docker file. Other kind of interesting commands include things like, the working directory. And again, working directory is exactly where the app code is going to go. Copy commands are interesting because what copy says is it says, effectively from this source on the host, copy into the container these exact files. Or I'm sorry, copy into the image these exact files. And so, again, if we had, maybe, some coin miners, or heck, maybe it's destructive ransomware. The point is those binaries, if there's full binaries somewhere, the way those artifacts get into the image is from this copy instruction. And over here in our working example, what they actually ended up doing was they said, hey, copy everything in the current directory into the working directory of this image. Next, we have a run command. Run command is the entry point for all my malware analysts. So when the image is first loaded into memory and it fires up, this is immediately the first thing that it does. It does whatever is behind this run command. You also have CMD. Those are kind of secondary things that are executing after the entry point, which again is the run command has been executed. And then finally, there's expose, and expose really lets us understand, this Docker, image when it's loaded as a container, if there isn't an expose command that's part of its, infrastructure's code, then no ports are actually exposed from a TCP/IP point of view. However, again, if you find this and there is a port exposed and conveniently that port connects back to the indicator of compromise that brought you to that host, hello, you might be looking at the right container. All right, let's talk about images. So we talked about earlier that, when it comes to, the Docker system components, again, typically images are stored at the registry. However, from a Docker engine point of view, they have to download the image before the image can be ran. And so those images are stored locally. And any images that are downloaded, again, unless your ops folks are really big into garbage collection and cleanup, which is typically not the case, you're going to see every version of an image that's ever been downloaded. And so, all of that is right off of, again, that var lib Docker. And then literally there is, whatever file system type is supported. And then right after that is, your repositories.json, which is really showing you, underneath the ImageDB folder, it's really showing you all the available images, what their exact configuration is. And again, that leads you to specific manifest files that tell you even more, such as, the exact history of that image, all the modifications that have been made to it over time, and again, anything that you saw in that Docker file, all that is recorded with timestamps in the actual, manifest file, for that image. And finally, there's something called image layers, and image layers are really, this is all those binaries, those libraries I was mentioning earlier that are loaded into memory. We saw in the example in the prior slide, just to kind of reference that again, that a Python base image was being used. And so we would actually see that called out. And then anything that was added from that copy command, as an example, would be another layer. And so all those layers are stored on the host file system, after that tarball, if you will, is downloaded, from the registry. Or if the Docker file is built locally, again, there is this layers folder where you can reconstruct the entire original operating system that was loaded into memory. I just want to point kind of to the right here. This is an example of what you might find in one of these manifests if you did go to one of the image locations. And, in this particular example, it shows kind of what architecture is expected. And you can see other interesting things like the actual host name, that was being used by the container. You can see things like, what the environmental variables were. We can see things like, the exact, image, the exact layer that's associated with, the image that we're looking at. We can even see every time an image was invoked in its exact identifier, which leads us into the next slide, where from a container perspective, again, because there is no garbage collection cleanup on these hosts, every container that's ever run is still sitting there. And you can see the pre and post file system right there on disk if you get a host. And so, the power of that is, when we think in terms of, where to find this, there's literally a var lib docker containers folder. And really from there, it's just, it's all you can eat, right? We can look at the logs. These logs are really verbose. If there was any web interactions, again, those are going to be recorded in a way that, that just we can read it without, special tools. We could see things like, what host name it had during runtime, what DNS it was using. We can see where its file system is. And the other neat thing, I mentioned earlier with the engine, that engine, all its runtime stuff is underneath this var run docker folder. Well, one of the child folders is the actual runtime environment, and run C was in my picture. I should have pointed a little more closely at it. But what you need to get from this is that if you get a disk and there was a live container running on that system, you can see the exact configuration of that within this blob. And it's all within this folder that sits on the disk. That is always there. If the container is live running, this exists. Go take a look at it. You can reconstruct what's live in memory based on what's at this location. Okay, moving along. So, and just to kind of build on that, everything I've told you so far really is down to, we're talking about what I saw on disk. Well, I think really what we need as forensicators is, what do we do if we're in a live fire event and, and whether it's a, compromise of one of our containers, maybe one of our, maybe there was container escape or hijacking of a host or whatever it might be. If our concern is that there are malicious containers, here's a process that I think would work in practice. If you know exactly the process that is connected to the malicious activity, go ahead and use a tool like gcore as an example and just dump that particular PID, okay? If you come into a live environment and you have no idea what the malicious process identifier is, then again, from my point of view, go ahead and capture physical memory. For most of us, I got to be honest, you're probably going to find that you're using this in a cloud environment, or there's probably going to be virtualization involved. And so guess what we're going to do? We're going to hibernate. We're going to snapshot. That's how we get that copy of memory. Don't even bother if you don't have to, with loading, some other third-party tool. Or if you have to, make sure you've got Lime or something else appropriately built for whatever the underlying operating systems are in that environment. Also, writing container to disk, one of the powerful features, and I wouldn't exactly call it a snap feature, but it's powerful in the sense that, if we've got our physical memory capture, we can now use a command with that Docker client. It's Docker space commit. And then we can give the commit command the exact container identifier. And what commit will do is it'll take whatever's in memory and it'll write it to disk for you. And then you have other tools that you can invoke, again, using Docker client, Docker export as an example, and that'll just take every component. And, earlier when we were talking about the container, I was telling you like 3, 4, or 5 locations you can check and many, many files. If you use the Docker export feature, it will now take that image that you just wrote to disk from the live running container and just put it in a tarball for you, which is really easy to pass off to, some security analysts for quick review and triage to figure out what's going on, which again can sometimes help when you're trying to, get containment on a fire. And then finally, again, I keep pointing back to, you're probably in a cloud environment, you're probably in a virtualized environment, snapshot where you can. If you can't, try to get a bitstream copy of the disk. As I was talking about earlier, anything that's going on in memory, again, it's being written to disk. Docker by itself does not have a great garbage cleanup. So if you can just get a hold of that disk, you could probably tell a story from, well, however long that host has been alive. Other things you should know, when it comes to, and now we're moving on here to, step 5. And really just what I want to point to here is, at this point, I'm assuming that you've already collected disk, you've already collected memory, and now we're really just in a position where we can, do some analysis, right? But step 1 through 4, that's an order of operations. Please do that first. Then we get down to, doing analysis. When it comes to examining, memory as an example, I mentioned earlier this var run Docker folder. Well, if there are containers running in memory, the way they pop up is literally as a process called Docker. And then if we look at, what file handles are open, there will literally be a file handle back to that blob I was talking about earlier. That is the full manifest for the running container. And that directory structure is very, very specific to the Docker runtime environment. And so it's easy to spot, if you will, what the active containers are in memory. Other places you can check, let's say you're in a more advanced environment and somebody was actually collecting logs and centrally storing them. You could also look environmental variables. And what's important about the environmental variables of these, user processes is that in the environmental variable, you will have the host name that's configured for that Docker container. And so you can look at the environmental variable for every running process to see other tools that may have loaded into memory, if the process was forked or anything. Again, you're going to see all the related processes, because the environmental variables will be shared across any new process that was created in addition to the Docker process. And finally, let's not just forget about our runtime libraries and such. Again, looking at our runtime libraries and handles, it kind of gives us a lot of clues where again, our Docker image was either working within the restraint of its namespace, or if it reached outside of its namespace and it was touching the host, again, we are going to see that, in our file handles, and we're going to see it in our handles, right? All those other outside interactions. Other things that are worth looking for too is network connections. Depending on how the compromise happened, there was an example in the timeline, I didn't speak to the detail, but there was an example in the timeline where a lot of the attackers were looking for the exposed Docker API. In 2021, 2020, there's a ton of examples where they're abusing vulnerabilities in the libraries that are part of the running container. And so what would happen is once the adversary found that you had vulnerable containers, they would attack every container that they could on the host and just compromise all of them. And so now their persistence is built on the fact that they're running on every container that's operating inside your IT environment. And so checking network connections is really helpful in the sense that, I feel like for a lot of the incidents I've worked, that when it comes to, or even sandboxes I've observed, it feels like, if there's one particular, bad connection coming in, if you see other connections from the same network, well, you kind of got a clue. You probably want to look at those too. Other things that are worth looking at is just checking for environmental variables in general. To me, we spend a lot of time, from a disk perspective, talking about, the secrets that are stored in Docker. We talked about, maybe, in the environmental variables, themselves, for the container, there could be sensitive data there. Well, the environmental variables for the underlying host, all that stuff's at risk too, in addition to the OS. If you are looking at, again, file handles and you see that there is interaction, on the host disk. And so just being sensitive to the environmental variables, I think is really key when we're trying to figure out, what's the blast radius if we do have a compromised container. And then finally, getting down to examining the host. Hey, this is just file system analysis. There's a great book out there by Brian Carrier. I feel like if you combine that with the cheat sheet I'm going to share with you, really these steps get really easy. We really, what we want to do, when it comes to compromised containers is, we do want to go find the original image if possible. More than likely, it's going to be on the system that had the Docker engine. And we just want to kind of compare that to, any of the runtime containers to understand, was it our stuff that got compromised, or our containers, or was the compromise a result of us having an unprotected Docker API? And really that's what was abused. Other things that are worth checking, I mentioned the containers have their own logs. Those logs are really verbose. They look like Apache web logs if you take a peek at them. Really easy to read. Other things that are worth doing is, just taking your timelining tools. If, what brought you to the event is a particular incident, at that point, whoever's on the team that's working with you, they probably got a date and a time. Hey, yesterday we noticed things were acting funny. Well, run your timelining tools. What's new from yesterday? And, use those tools not just against the host, but also use them against the underlying file systems that were part of those containers, especially if the containers are what's in scope for the incident. Finally, just kind of, bring us here a little bit to an end. I mentioned, doing this whole diff-based analysis. I really think, what's key with the diff analysis is that, if you have the image on disk, take a look at that. If the image is not on disk, but it's running in memory, that's probably the bad container. So, all right. So sorry. One other thing, if you have again, a malicious container running in memory and you don't have an image on, again, that earlier opportunity identified with use of things like curl or git, do take a carve for those and see if you can find where the adversary sourced their image from, and you might be able to still grab a copy. Definitely talk to your legal team before you do anything like that, but again, you might still be able to get the image. All right, so just kind of moving on to some tool options. I'll try to show some of these. I gotta be honest, folks, there's a lot here. I'd rather you have the slide deck and go out on your own and kind of experiment a little bit. Some of the stuff that's here are things that have been out there for a long time. Some of it is new and just really specific to Docker. Just kind of, top to bottom look here, from a memory capture point of view, I mentioned G-Core, I mentioned Lime. There's also something called CRIU and CRIT. And what this is supposed to invoke is creating an ability for you and your operations team to actually create snapshots of images. I think it's later here in the list. Matter of fact, it's right over here in memory analysis. With CRIU, there's a tool called CRIT where you can do, memory type analysis against these snapshots. With that being said, this does take some setup and configuration. And in my opinion, this might be, a very coordinated effort. My experience was, I don't think this is something that you would just whip out there during an incident. However, when it comes to G-Core, that's probably just available to you. And Lime, we can build Lime in advance before we get onto any incident, if that's even necessary, because our last item is, as I mentioned before, most of these cloud virtualized environments, they're snapping, hybrid features. Go ahead and take advantage of them. That's really how you're going to get your memory. And this way you're not introducing software after the fact, which is really just going to contaminate the pool, right? And I'm sure you'll have plenty to look at when it comes to a compromised host. When it comes to disk or container collection, other things to think about include things like using, maybe the native Docker tools. I kind of gave like an order of volatility type approach on the previous slide. And again, I mentioned, using native utilities, whether it's disk or memory, all those things can be snapped. And then finally, in your worst case scenario, use tools like, DD or EWF as an example to go ahead and get your forensic copies of disk. Again, I think these days are a little behind us with the modern IT environments, but have these at the ready and know how to use them just in case you get into, as an example, maybe a big old hunking piece of metal that is not virtualized, and now you got to do stuff by hand. Go ahead and be practiced with this before you get into that situation. When it comes to image analysis, some tools that I thought were cool that I came across just looking at some of the public work out there. There's a tool called Whaler, another tool called Dive. These aren't really traditional forensic tools. I think these are meant more for developers to do analysis. But I got to tell you, they got some great features as far as presenting things in a way that it's easy to do analytics on, the history of an image and what the actual manifest of an image is. Also, Docker inspect, Docker diff. When it comes to just using native Docker tools. If you're mounting, let's say a captured, disk from a compromised host, you have the local Docker tools. You can still, mount that disk, on a loop back, make sure it's make sure it's write blocked, and then use Docker inspect and diff, on the Docker, repos or the local image store. Just see what changed from, the version that you suspect was compromised or the version that you think was attacked versus, what's on disk. When it comes to container analysis, again, we have a lot of great options, and folks, I'm going to speed it up here a little bit, but Docker Explorer, there's Docker Forensic Toolkit. And again, these are purpose built to look at containers, and these are our actual forensic tools. You can see one's made by Docker. It's a wonderful tool. And really the rest of this is just kind of speaking to other reading opportunities, and you'll have access to that at the end of the talk. I just wanted to take a quick look here at one of the tools. And so this is, I'm invoking the tool Dive, and really what I want you to get out of this is me using a tool called JQ, where I'm reading the manifest, if you will, for what images are on disk. And this is all the possible images that I could be looking at. And again, this is just me using a JSON reader to read what's stored locally. And here I'm just highlighting that the latest image has this identifier. Well, I can go out there and I can go read and see what's inside of that exact folder, again, using JQ, which is changing that JSON into something that's a little more, reader friendly. And again, you can see that everything within that image is timestamped, when it was added, and exactly, what was added by that Docker file that we were talking about earlier. Now, the issue here is that everything is happening in the command line. Now, if we use a tool like Dive as an example, what Dive brings to the table is our ability to now see this. We're in a GUI type interface. And I think, if we're not used to being in the command line, I think this is great, because now we can kind of click through each little layer, starting from that base image that the image we're looking at now was built from, down to what's happened over time and what commands were executed in order to bring that image into its current state. And some other things I'm not going to show here with this is that we can actually see things like what files were added for each one of these layers, and even look at the individual files as they were added in order to make that particular image. Another tool that I just wanted to share, hopefully it'll let me share it with you. Okay, here we go. And so this is an actual Docker forensic tool. And so where things change, Dive was not showing us really all the timestamps that are available. And so in this example, I'm actually using the Docker forensic kit. And I'm just showing that there's a lot of different commands that you can invoke. And the way that I'm approaching this as far as the execution, again, I'm listing all possible images that are on the disk. I'm going, oh, well, there goes that same one I looked at earlier in JQ. Again, the format here is a little more friendly. We can easily see that there's been two different containers that have been created from the image that's stored on disk. And so if I wanted to immediately pivot to the containers that executed, I can clearly see them right there. Versus earlier when we're looking at, the stream of text, I feel like you really would have to train your eyes to know where to look. Versus, this tool is showing you. Another thing I'm not going to show in this demo, this tool does, it'll even go out there and it'll say things like, okay, you've got 3 containers that don't have images on disk. Hello, that is not how a normal environment will operate. And so, that would be just statistically a quick clue where you can go, hey, you know what? This is probably a compromised machine. And again, just think back to, when I was mentioning, the fact that there is no garbage collection or cleanup, right? All this stuff is being kept out there. So if you see a container, if it's legitimate, there's going to be a pairing image. If there's no pairing image, that's probably the bad one. Some other things that are going on here on the screen is just that it's showing more in a log-esque type format, all the changes that have happened when they've occurred. This is much, much more verbose than Dive. And again, it's because it is a forensic tool. There's a lot of other features here that I'm invoking, and it's going to take us a couple more minutes to go through them. But I think the key thing is that what I've been describing as far as the fact that images become containers, and that when it comes to containers, you have both the original file system from the image that was loaded up, but you also have recorded on the disk whatever modifications that were made to the file system. And so all that, from a forensicator point of view, puts you at an advantage and allows us to get to the highest level of the pyramid of pain, which is identifying the TTP of our adversary. So you can either disrupt their activities in that moment, or again, resist them from, future efforts to compromise whatever the weakness was in your environment that presented them with an opportunity. Next talks, again, if this one excited you and you think this content resonates with you and helps you on your job, I am thinking about doing a talk on analysis of a compromised container and what that looks like, and what we will be, doing an accepted reverse engineering methodology. We're also looking at kube forensics, or if there was some other orchestration type environment you want me to talk about forensics on, that's definitely an opportunity. And of course, we do want to get into, SaaS type forensics, as we start, using this stuff out in the cloud, what does that look like? And then also full CI/CD analysis. You heard me use some terms earlier, like Git, which is, a VCS, type thing, artifact repo. These are all different places with different forensic artifacts that can really help you retell a story if you do have full environment compromise. All right, folks, thank you so much for your time. Thank you for listening. I know this one was a little bit longer than usual. Do we want to keep the recording going for questions, or do we want to cut that off so folks can kind of speak freely?
Yeah, we can go ahead and cut that off, and then